Astrology. Thank you for Professor Yara Astrology for the invitation. So then I share the token. Yeah. Mm. 对，请回忆报告。Okay. Yeah. Then I talk about little this model structure. So with this classical homological, 有声音吗？Dimension. So this projective dimension, uh, flat dimension. This is PGF. PGF is a module. 看不到屏幕。You can see the screen?
I can see your screen, but the PDF file is not open now. You should, I think.
Not open. Okay. So what's problem? Yeah. 重来一次。停止。然后再重新。那么应该是这个Hello, line is okay?
Just a moment. Yes. Now it's
Located.
okay.
It's okay?
Yes, it's
Okay.
okay.
All right. So I will talk a little about this mode structure. So this with the classical homologic dimension. This is a project dimension, flat dimension. This is called PGF. PGF is the name of module. PGF dimension. This is Gorenstein projective dimension and Gorenstein flat dimension. So in modular category of a ring or in this exact category. This exact category means, for example, PGFA means the module with PGF dimension no more than n. N is a non-negative integer. So this is the class of module. GPA, it means the class of module with the goals and projective dimension is no more than n. Yeah. All these are exact category. In this 6 exact category, we will obtain new model structures and to determine their homotopy categories. Okay. So recall what is a model structure. A model structure on a category is a trip of 3 classes of morphism. The morphism in cofiber is called cofibration. The morphism in fiber is called fibration, and morphism in weak is called weakly equivalence, respectively, satisfy these 4 axioms. The fact is 2 out of 3. That is, if we have 2 morphisms composable, F and G, then if 2 of F, G, and the composition are weakly equivalents, then so is the third is also weakly equivalence. The second is called closed and retractors. That is, if F is a retractor of G, this means here is morphism G, here is morphism F, then there is a commutative diagram such that this phi 1 and psi 1 is identity of X, and phi 2 psi 2 is also identity of Y. Yeah, this means F is a retractor of G. Then if G is a cofibrillation, then F is a cofibrillation. If G is a fibrillation, then F is. If G is a weakly equivalence, then so is F. The second. The third one is for any this commutative diagram, where this I is a cofibrillation and P is a fibrillation. If I is again equivalence, or if P is equivalence, that is, if I is a trivial cofibrillation. By trivial cofibrillation, we mean I is a cofibrillation and I is in weakly equivalence, or P is a trivial fibrillation. That means P is fibrillation or P and P is weakly equivalence. There exists lifting from B to X such that these two triangle commutes. That means IS is A and SP is B. The last one is any morphism has two factorizations. That means F can be factorized as I P, the combination of I and P, where I is a trivial cofibrillation and P is a fibrillation. Another factorization is F can be written as the composition of G and Q, where J is a cofibrillation and Q is a trivial fibrillation. Yes, this deflation, this system is given by Daniel Quillen in 1967. So this model structure is at that time, now is the main theory and tool in topologic in mainly theory and tools in categoric topologic theory. Is categoric topology, yes. But now, as the development of representation theory of algebra, it also, a lot of interaction, So, giving a model structure on a category, we have 10 class of object of studies. Okay, we consider the category with 0 object. Then this is so the first this is 2 class of in the definition, morphism, and this is intersection. It's called class of trivial cofibrillation. This is a class of trivial fibrillation, and this 5 class is a class of morphism, and we also have 5 class of objectors. So by C, we denote the class of cofibrillant objectors. That is all the objectors such that this 0 morphism from 0 to X is a cofibrillation. This is the class of fibrillant object, that is all the object Y, such that Y to 0, this is 0 morphism. This is a fibrillation. And the class of trivial objectors, that means all the objects W such that zero W, this zero morphism is weakly equivalence. This is exactly the class of objects such that W to 0 is weakly equivalence because this weakly equivalence has 2 of 3 property because 0 to 0, this identity is always weakly equivalence. And then we have this intersection. It's called trivially cofibrant objects. And this is trivially fibrant objects. We have these 10 things. Another important concept is homotopy category of a model structure. So by definition, the homotopy category is just the localization of M with respect to the class of weakly equivalence. So, okay, as you know, from the classical theory by Gabriel and Zisman, for every category and every class of morphism, this localization of category is always exists and unique. Yeah. Okay. Then the fundamental taskers say we want to try to get a new model structures to study these properties of model structure. In particular, these relations between these 2 classes of object of study. Yeah, and one of the most important things is the structure of this homotopy category. Yes, this homotopy category of model structure is one of the most important things in the theory of this model structure. So now any triangulated structure we know can occur from this homotopy category of a model structure. Yes, in algebra at least, yes. But usually this homotopy category is not triangulated, but it's called pre-triangulated. Okay. That's as a setting up, we talk a little about exact category. I will not repeat this system or axiom of this exact category. Okay, I write in here, but let's emphasize that this exact category, as you know, is quite necessary. It is a generalization of abelian category. Yes. Any what we need is any 4 subcategory of abelian category which is closed under extension is exact category. Yeah. So in order to work in exact category, in representation theory, we usually assume this weakly exact category should be weakly idempotent. This means in this exact category, so any splitting epimorphism has a kernel, or equivalently, any splitting monomorphism in A has a cocolor. In fact, the most exact category we know are weakly idempotent, but it really exists exact category which are not not weakly complete. Yeah. So in fact, all 4 subcategory of abelian category, which is closed under extension, and direct summers are weakly idempotent complete exact categories. Yeah. So, for example, this PA are weakly idempotent complete exact category. So PA means a modulus of projective dimension, not more than n. Yeah, this is all this Goranson projective module or this Goranson flat module are all weakly complete exact category. Also, this GPA and GFA, this means all the modules of Goranson projective dimension not more than n is weakly complete exact category. Okay. Now we talk about a special model structure, which we call the exact model structure. Exact model structure is over an exact category. So a model structure on an exact category is called exact model structure, provided that this cofibrillation is actually this inflation. Inflation, that means just you may consider this in ability category just monomorphism, okay? Such that the coconut F is a cofibrant object. We have talked about cofibrant object. This coconut F is a cofibrant object, and the fibrillation is exactly this deflation. That is epi. You can see in ability category the epimorphism, such that the kernel is a fibrant object. So in this case, this trivial cofibrillation is actually, this coconut is a trivial cofibrant object, and trivial fibrillation exactly this morphism that such that the kernel is a trivial fibrant object. Now we emphasize that this if the category is abelian, then this model structure, exact model structure, is just called abelian model structure. So we stress that not all the model structure on exact category are exact model structure. Exact model structure on exact category only some very special model structure on exact category. But this special model structure is of greater importance because of this result. That is the homotopy category of an exact model structure on exact category is clear. That is, it is just the additive quotient. So this is C intersect F. So C intersect F. C is the class of cofibrant objects. F, as you remember, is a class of fibrant object. This is the quotient with respect to these three intersection. This W is the class of fiber object. And the most important is it is a triangulated category. So this is quite a new result. For example, in this year in Gillespie's new book. And of course, in 2019 is in their paper, Nagaro and Polo, their paper for extra triangle category. They have this, but this proof in this book is more understandable. Yes. Okay. So in fact, at the time of Quillen, all the model structure mm, from algebra side are exact model structure in Quillen's examples. Okay, then Hovey summarize this and give this definition of abelian model structure, and Gillespie extend this notation to exact model structure. Okay. Okay, then the main problem is how to construct the model structure, especially exact model structure. Yeah, this we are closely related. So called contortion pair, as you know. So contortion pair in exact category is a pair of objects such that this C is left perpendicular of F. So this perpendicular is just for extension 1, and F exactly the right perpendicular of C. Then a contortion pair is called hereditary if C is close under the kernel of deflation and F is close under co-kernel of inflation. Yeah. And another fundamental problem is the contortion pair is complete. That is, for any object, you have such an exact sequence in this exact category, such that this C is in C and this F is in F. And also an exact sequence that is here F prime is in F and C prime is in C. So this is the two main concept of contortion pair, hereditary and complete. Then, as you know, we have this important Hovey correspondence give the construction of exact model structure. So we call that trip XYZ in exact category is a Hovey trip. That means these three are class of objects. That the Z is seek means Z is close and direct summers, and any two terms in exact sequence, in Z, they so is the third one. Yeah, this is called seek, and there are two complete contortion pair. Complete contortion pair. That is, if X intersect X, so X intersect Z, and with Y is a complete contortion pair. And also, this Z intersect with Y, so X, Y, Z, this is also a complete contortion pair. This is by definition the Hovey trip. Then the main theorem said that for a weakly idempotent complete exact category, then the exact model structure of this category are in one-to-one correspondence with Hovey trip. Yeah, that is, if you have a exact model structure here, then you just map it to this is C, this is F, this is W. So C is just the cofibrillant object. F is just a class of fibrant object, and W is just the class of trivial object. Then it is a Hovey chip. And conversely, the inverse map is given by if you have a Hovey chip of this chip of class of objects, you get cofiber, fiber, and weak defined like this. This is in construction way. So the cofiber is just all the inflation with coconut in X, and fiber is just all the deflation with kernel in Y, and weak is just the composition of inflation such that this coconut I is in X intersect Z and here, and this P is just deflation. The kernel is just in intersection of Y and Z. Yeah, this is the composition of I and P. Okay, then by this result, from now on, we will identify exact model structure with a Hovey chip. Yeah, with a Hovey chip. And this more exact model structure is called hereditary if these two quotation pair are hereditary quotation pair. Yeah. Then we recall, yeah, this various Gorenstein projective module, and we know this our colleague, yeah, yeah, in your group has a lot of work in this side. Yeah, so we just recall a module is a Gorenstein projective module. So it is a usage of this double infinite exact sequence of projective module such that M is image or is a kernel of a map. Yeah, such that is after for apply functor home functor. So at the second position for any projective module Q, it is still oh, I miss here. It is still exact. This is still exact. This is exact. I missed to write. It is exact. Okay. This is Gorenstein project. Then similarly, we have so-called Gorenstein flat. That is the usage of exact sequence of flat of all these flat module, such that again exact after tensor with any right injective I module. And this is a new, in some sense, it is called a PGF module. PGF module is a mixture of Gorenstein project and Gorenstein flat. That is called, in Forlem, called the projectively co-resolved Gorenstein flat. That is usage of exact sequence of projective module. But which is the exact after tensor with any right injective R module. Then we know this PGF module is Gorenstein flat and also Gorenstein projective. Yeah. And this PGF module is the exact Gorenstein projective if and only if this Gorenstein projective is Gorenstein flat. This PGF module is introduced by Saro and Storici in 2020. Yeah. As you know, it's a bigger problem. It's open. So a long time, for a long time, whether or not a Gorenstein project is Gorenstein flat. As you know, projective is always flat, but the Gorenstein projective, whether or not it's Gorenstein flat, is a difficult problem. And also, whether or not this Gorenstein projective is PGF. This is also not knowing, but these two things are equivalent. Yeah, as you see here. Okay, then we consider various dimensions. By here we call the GPD. This is Gorenstein projective dimension, and this is the PGF dimension, and this is projective dimension. They have this fundamental relation, and we have this also this fundamental relation. All this immediately follows from the definition. Yeah. Okay. Yes. Now we see this table. Yeah. We summarize all the knowing results in a modular category about uh, uh, contortion pair and Abini model structure, or you call the exact model structure. But in Abini category, in model category, we call the Abini model structure, the same things. So all this this things in red is means the lowing result. Is the lowing result. Let's see. All these pair are hereditary complete contortion pair. So for example, this P R mod, this is trivial, but this is not so trivial. This is a flat module. This is called a contortion module. That is, contortion module is just the right perpendicular of flat module. This is a classical result of inox and red. And this is also the PN and the PN perpendicular. This Fn and Fn, this also hereditary and complete contortion pair. As you know, not any contortion pair can produce a model structure. A model structure requires more strict information. Yeah. So as you see, we need the Hovey trip to get model structure. In their paper, Sarah and Zovici, they give this is a model. This is a hereditary and a complete contortion pair, and they give this is a Abini model structure. This is given in Hovey trip. So you see this intersect this. This intersect this is just a projective module. So it is this contortion pair. And this intersect this, of course, is still this. This is all the module. So it's still this. So you see this is a Hovey trip. So it gives a Bini model structure. And this is the result of elegance and heighting. So this is contortion pair. This contortion pair is not easy. It is only now works in Artinian algebra. Not is for any ring, but here is for any ring. This is only there's here is a big problem whether or not this is works for any ring. This is open. This is open. But for Artinian algebra, they mainly use this the duality in Artinian algebra. They have also this Abini model structure. Okay. Then for Gorenstein flat, they also have this model structure. Then also on 2023, this they give for this result. When we collect all these results in one table, then we found all these are problem are empty. Yeah. So then we naturally ask her, what is the situation here? And we are lucky we can complete this table in the follows. Yeah. So the first to see the Albini model structure arises from this PGFA and GPA. That is for any ring. This is hereditary complete quaternion pair in modular category. The intersection is and this is also then this quaternion pair can form exact model structure. Yeah, and this model structure is hereditary. And we can also compute their homotopy category. So this is just a PGF modular P. This is the triangular category. You see, this homotopy category is independent with N. They all are same with, yeah. Also, for Artinian algebra, we can talk about, this GP. Yeah, then we can complete this table, all this table. Yeah. So, in this, okay, if you see here, this is exact model structure. If this intersect this, this intersect this, this is just PA. So this is quaternion pair hereditary and complete. And if this intersect this exactly this quaternion pair, so it is a whole chip. It gives a Albini model structure. All are the same. So yeah, okay. Then this is a model structure. This table is a model structure in modular category. And now we are talking about this model structure in exact subcategories. So this depends on keen observation. We call the keen lemma. That is, if A is a Albini category and B is a full subcategory of A, which is closed under extension. Yeah, of course, then B is has natural exact structures. So suppose that XY is a complete quaternion pair in A, such that this X is contained in B, and B is closed under the kernel of epimorphism. Then at restriction to B, this X, Y, B is a complete quaternion pair in B. And if original quaternion pair is hereditary, then this restriction in B is also hereditary. So let me stress that usually this quotation pair in A can never restrict to its subcategory such that it is a quotation pair in B. Yeah, but with this quite strict conditions, it can be, yes. This is the main method we obtain this quotation pair in exact subcategories. So remember, we have all this quotation pair, then we try to use this, apply this lemma to all this exact category. So for example, in PGFA, this is a class of module such that the PGF dimension is not bigger than N. Yeah, this is exact category. Yeah. Okay. Now, as you may see, so we have this hereditary complete quadrant pair XY, yeah, such that this X in PGFA. So that is, this is PM and PM perpendicular, and also this PGFM and this here M is smaller or equal to A. Yeah, this already given in this table. Yes. Then we apply this kin lemma. Yeah, I repeat this kin lemma. Then we get this one. Yeah, get this. Yeah, then this get this model uh, structure in this exact category, and the homotopy category can be also calculated, yeah, in this. It is, in fact, it does not depend on M and N. So then we have two chains, one parameterized by M, another chain is parameterized by M. So with the semi-homotopy category, which is triangulated, yes. So also this is in GPA, yeah. This is in GPA, yes, with the semi argument. But now we see another model structure on GPA. Yeah, this is for any M and A with M smaller a. Then we say this is GPM and this is a hereditary complete quadrant pair in GPA with intersection is this. And this gives Hovichip. Yeah, this gives the Hovichip. So if you intersect this with this, yeah, this is if you intersect this with this is just GPA and PA intersection is just PA. So this is exactly this. And if you include this and this is just the quadrant pair we have obtained in this PM GPA here, if you remember, but here. Compare something in here, something in here, yes. But so their form also a Hovichip. So they give a hereditary model structure on this exact category. This is a homotopy category. Okay, why I stress this? Because this is not obtained, applied the kin lemma to this complex category. The way we get this is quite different, and the proof of this result is also more difficult. Yeah, not by applying the kin lemma, because here I is a ring, not Artin algebra. And so I stress here in Billigins and Ratings result, this in A0's case, this is for Artinian algebra. It cannot be for any ring. But here we can for any ring. So this use a different argument. Then we can complete this we can complete this table. So here also with this red one, this knowing result, of course, this is true. This we have this all these are in exact category. If you see this table, for example, this is in GPA, this is in GFA, this is in PGFA, yeah, this is in F infinite. That means all the module with flat dimension is finite, and the PGF, yeah, small infinite, and this is in all the modules with Gorenstein projected dimension finite. Yeah, all these are exact category. These pairs all are hereditary and complete cotortion pair, and all these trips are Hovey trips. That is all the exact model structures. So, for example, in this GPA, we have two different yeah, this is a model structure. This is another model structure here. This is a model structure. This is the trip, and this is also a trip. It's another model structures. Yes, with two different model. Yes. So then the knowing that I use in color. So in 2022, these two French mathematicians they give this result in Gorenstein flat module. In this exact category, they have this Hovey trip. And yes, okay. Maybe I just stop here. So thank you very much. Yeah.
Oh, thank you very much for your very nice talk. Thank you.
Thank you.
Are there any questions or comments?
Actually, maybe I can start with a very naive question. Thank you very much for your nice presentation, Paul. Do we have a model structure starting with the inox flat cotorsion pair? I mean, does this cotorsion pair include in a model structure Hovey triple?
Sorry，我还没有听懂他的问题，他什么？Could you repeat? Let me 我来把这个声音变大一点，怎么的？Could you repeat the question?
Yes,
just
yes. Actually,
now
we have a.
the
Okay. Can you hear me?
I get a big. Yeah. Okay.
Okay. We have a cotorsion pair by flat and cotorsion modules, inox cotorsion pair. Yeah.
Yeah.
This is a famous complete cotorsion pair, hereditary complete cotorsion pair. My question is that I forgot, does this cotorsion pair includes in a Hovey triple? Do we have a Hovey triple containing this cotorsion pair? Or
yeah, not every protortion pair can be complete Hovey trip. Yeah, as you know. For example, here this protortion pair we have no no trivial Hovey trip. Yeah, arising from here. So now we have only this covalent pair, but it cannot form a Howey triple. That is, it cannot form exact a model structure. Yeah.
Model structure. Yeah.
Yeah. But you can always get a trivial model structure. That is not of interesting because you take just the trivial object as is all the module, for example, is all the category. So in all the categories, then the corresponding model structure that is homotopy category is just 0. Yeah, we are interested only the model structure such that the homotopy category is not 0. If the homotopy category is 0, then we think this is the trivial situation. One has no interest on that. Yes.
Yes. Okay. Thank you. Thank you.
Yeah. So the Howey triple, yes, in some sense is yeah, is a little strict because it is not giving itself by 3 class, but it's just the intersection is yeah. As you know, the intersection, this intersection, yeah, is complete quotation pair. Yes.
Yeah.
So are there any more questions or comments?
Maybe I can ask another question. Sorry, you didn't say anything about Gornstein injective modules. Does there are something similar theory for them?
For Gornstein project.
No, Gornstein injective modules.
For Gornstein project module, right?
No, I mean Gornstein injective modules. You said
Oh,
about
yes, you are
projective
right.
and
This is
Gornstein
the
flat.
dual version. I did not talk about the dual version. You are right. There is a dual version for Gornstein injective module. Yes. And as you see, I did not talk about the injective module and also not talk about Gornstein injective module. Yes, this is a dual version. There is a corresponding version. Yes. Yes.
So any more question or comments? So seems there's no. Let's thank the speaker again. Thank you very much.
Okay, thank you very much. Yeah. Okay.
Yeah.